Well, thank you for your continuing and kind attention. I think this will be the last video we'll need in this immediate topic, but we are doing estimation. We're trying to estimate mu, that is the average of the population. And just to have an example, we said the population of hat sizes. So suppose now that we go ahead and we take a sample, and we'll make this up. We're not really going to be taking a sample. But maybe we'll take a sample of size, I have this written down here somewhere. Maybe we're going to take a sample from this population of size n equal 36. And suppose then on that sample we find that x bar is equal to 7 1/8. That's an American hat size, maybe a British hat size. I doubt it, however. I think they're probably going in centimeters. And 7 1/8 would be, as a decimal, 7.125. So there's our value for x bar. Now just suppose further, we've got our sample of size 36. We've calculated x bar. Let's calculate s, and s is the sample standard deviation. And just say, so that we have a number there, s is 1.2. Now what we want is a 1 minus alpha confidence interval. Let's just suppose that the confidence we want to have in this estimate of mu is 95% confidence. So 1 minus alpha then would be 0.95, which means that alpha would be 0.05, and alpha by 2 would be 0.025. Now, we've calculated those before. The critical value we're going to need for this estimation, let me sketch again, student's t distribution, which looks very, very much like a z distribution. Right here under that highest part would be 0. And over here, we've got t. Now, our alpha by 2 and degrees of freedom would be degrees of freedom. And I'll go ahead and write that since we're just starting here. Degrees of freedom would be 1 less than the sample size, so the degrees of freedom would be 35, and the alpha by 2 would be equal to 0.025, as we've just calculated above. And this would be student's t with degrees of freedom equal to 35, 1 less than the sample size. And we need to find this. This is a critical value. That's our critical value. And so how are we going to get that? Why don't we use our graphing calculator? Got to find our graphing calculator and then we can use it. So here's our graphing calculator. Distribution, so we'll say second distribution. We want the inverse t because we want to find a critical value, so it's 4. The area to the left is 975. The degrees of freedom, well, we said we've got a sample of size 36, so our degrees of freedom would be 35. And we will enter that, and we'll paste that result into our work area. You can see it. We'll hit enter again, and it calculates 2.03. So that critical value is equal to 2.03. Now we know our 95% confidence interval is going to be x bar plus and minus the maximum error of the estimate, plus and minus e, where e is equal to t alpha by 2. It's very common to leave off degrees of freedom as long as it's understood what the degrees of freedom are. T alpha by 2, s over the square root of n. And this would be, well, the T alpha by 2 we just looked up is 2.03. And S, we calculated that from our sample. Our sample was of size 36, and S was 1.2 when we calculated it. So that would be a 1.2 divided by the square root of the sample size, which is divided by 36, is equal to. So now we've got just an arithmetic problem. We'd use our calculator and we'd calculate 2.03 times, this would be, since the square root of 36 is 6, this would be 0.2. 2.03 times 0.2 would be 0.406. So that's E, the maximum error of our estimate, or sometimes called the margin of error. Now, what is our confidence interval? Our confidence interval is going to be X bar. That would be 7.125 minus E, 0.406, to 7.125 plus E, or 0.406. So this is a 95% confidence interval estimate of mu. We can be 95% confident that mu fits between those two numbers. Now, I think we could and should clean that up a little bit. So when we clean that up, these two numbers are 6.719. You can verify that, and you should verify that. 7.531. So this is our 95% confidence interval estimate. And let's take just a second and talk about what does that mean, 95% confidence. It means if I would repeat this procedure, take a sample of size 36 and calculate a left-hand endpoint and a right-hand endpoint just as we did before, we would get slightly different numbers here. Now, why would we get slightly different numbers? Because if I take a different sample, then X bar is going to be different, and S will be different, and that's going to give me a slightly different left-hand endpoint, right-hand endpoint. Suppose that that new interval that I get ranges from there to there. We won't put numbers on it, but they're going to be close to these two, but not exact. And suppose that mu is right here. Then I want you to do it again. Take another sample of size 36. This time you may get an interval that looks like this. Do it again. This time you may get an interval that looks like this. But if this is where mu lives, notice that in each of these cases, although we've got different intervals, we were correct in that mu was between the left-hand endpoint and the right-hand endpoint each of these times. Now, once in a while, we're going to come up with a sample that gives me an estimate for left-hand endpoint, right-hand endpoint that maybe looks like this, and you can see that, well, this time we were wrong. We didn't capture mu in here. But what we know is if we've got 95% confidence in the procedure, we know that we're going to be correct. That is, we'll capture mu. We're going to be correct 95% of the time. And that's a 95% confidence interval. Now, you'll read your textbook. I'll give you the pages, and you will work some problems, and then you'll be an expert on confidence intervals for the population mean, mu. Thank you. Be with you again a bit later.